structure of this will be, we will, or Daniel will, walk us through the theory. Robin already walked us through a little bit yesterday. He's going to walk us through more theory of molecular networking. But first, we're going to set up the workflow and get that running so that by 2/3 of the way the session is done, our data files will all be finished, and then we can look at the data together. So hopefully everyone is connected to the internet, not having problems. And let's just dive right into it. So everyone should have hopefully created at this point now a GNPS user and information. So navigate to the GNPS homepage, and we're going to kind of walk through how we run the data. Have they uploaded any data into their profiles or not yet? Do you know if have they updated data to their GNPS usernames and things like this or not yet? Okay. Okay. So hopefully you've navigated. This is what the original GNPS interface looks like. There's of course the GNPS2 user face, but there's less available there. So the basic structure is you have some of the standard data analyses, like classical molecular networking. People ask me a lot, should I do classical molecular networking, feature-based molecular networking? My advice always is if you only have two variables you're testing your data against, or you have single data files, classical molecular networking works really well and it's fast. It will do all the same functions that we'll do with feature-based molecular networking, but there's a limitation on how much metadata you can actually mine against. But you can also do library searches, for instance. You just input your single data file and you search against the libraries. And then there's loads of in silico tools and advanced analyses that you can conduct. But we're doing feature-based molecular networking. So, for instance, here on the homepage, I'm logged in. I'm going to do feature networking. So I'm going to analyze. It's going to pull up a workflow page. Two huge advantages in GNPS are that although there is data limits, every workflow you run can be accessed with the Jobs tab. And so you can find old data sets, rerun them on new workflow updates. Also, I meant to put a slide in here about data privacy. So if you work for industry or you're worried about data privacy, so GNPS does not mine any of your data unless you make it publicly available. So your account is private to you. GNPS cannot access that data in any way. So if you have samples from clinical studies or anything like this, the data is private. Only upon depositing a massive data set and making it public does it then become mineable by GNPS. So you don't need to worry. There's also lots of stuff about privacy in the documentation that you can read more about if you're worried about using this. So here's the workflow, and I always advise people use the documentation that's available. Super helpful, walks you through every single step. In this case, we'll give it a title. So I'm just going to call it SSI Summer School example. You guys would call it SSI Summer School Group 1, so on and so forth, whatever was appropriate for your own data. And then here in this section, in the file selection, this is where we're choosing all of our outputs from MZMind preprocessing. There are other preprocessing tools as well, like MSDial, and they provide all the same file types. They all, I believe, have specific export functions for feature-based molecular networking now, so you don't have to fight it. This is what an upload looks like. So if you were logged in and your data was present into your user file, it would be present under this username. If the files were also present in the massive data set, I've actually pulled it up using the shared file function. So you can go to share files, type in the massive data set, it'll pull it up for you. But these MGF files aren't present in the massive data file. So we'll do it the old school way. You see I have lots of options over here. In this case, I'll pull up my user tab. Now, if you were to pull up yours, you would only have a little bit of data if you've just made your user account. I have loads of data here, so I have to navigate to the folder that I have. So I've made a subfolder in here, Summer School, Copenhagen. And then I have all of the data files for the different examples. And now I need to select the files that go into the appropriate fields. So I'm going to do the example. So in this case, we have 3 file types and we have a metadata file. And all 4 of these files are integral to running the feature-based network. So the MGF file is the file that has all the information of our features. So this goes into, thankfully, appropriately titled MS2 file, MGF. We'll drag and drop it. So if you highlight the file and then you just click and drop it into it, we'll navigate back down. You have a quant file. It goes into the quant location. And then this last file, which is named MS annotation. This is a product of ion identity molecular networking that's conducted in MZMine. And this is the information that has links to say, this node is linked to this node and they're adducts of each other. So if you don't include this, networking will still continue, but you'll lose those annotations and they might be set off as singletons. And then this is dropped into the additional edges from external tools. And don't worry, there are screenshots in the PowerPoint that will be available, so it's easy to follow through all these steps. Yep, and then last file is the metadata. So this is the information that's adding context to the study. Without the metadata file, it's just a bunch of file names and a bunch of features. You might not be able to gain any context from it. So in this case, we want to evaluate the different parts of the body that the swabs were taken from. Without the metadata, we wouldn't be able to do the study at all. And that's the super important thing. The metadata is key. You add as much metadata as you possibly can. And then there's a sample metadata field as well. Yeah. So these are the 4 files that you really need. You can also add the original MZML file into the workflow if you have it available. In this case, I don't have them uploaded, so I won't add them here. Don't use the Google Sheets metadata anymore that's available here. I don't think it's operational anymore. And then you have all of these fields down here that have individual settings for molecular networking. You can play around with them if you want, but the most important thing are these basic options, and that's why it's not collapsed. So in this case, we have to choose MZMine as our quantification table source. You can see that there's all these other potential programs that will generate the same type of files for you to choose what's appropriate for whatever you're using. I think because you guys have all used MZMine, it's probably the preference you will choose. And then these precursor ion mass tolerance and fragment ion mass tolerance. So these are both settings dependent on the instrument you run your data on. And in order to conduct molecular networking, you don't have to run on an accurate mass instrument. You can run on a low-res instrument and still run these workflows. The most important thing here is that you have to tell the workflow how much, to what level of tolerance you can do. And if you highlight over any of these fields, it brings a pop-out bar that explains anything you can change in there and what the recommended settings are for. So for instance, here it says the default value is plus or minus 0.02 for high-res instruments. And you can drop this lower if you have an orbit trap, high resolution down to 2 ppm or something like this. Or if you have low-res instrument, I think it says 2 Daltons. So, but you can see how that wide field will potentially affect your data. So in this case, we're going to leave it at the standard settings. We could drop it a little lower if we wanted, 0.01. Sometimes I run workflows 0.005. But this is really the key for when we generate networks. That way we don't combine too many features into a single node. If we do that, then we're convoluting our data. Yeah? Everyone following along? No? Okay.
Is it getting the data in?
Okay. So let's explain getting the data in.
The drag and drop.
The files might be too big. Okay. Yeah. So, okay. So for those in the Zoom call, we have to upload our data first into any of this stuff. So into user. So there are two ways to do this, through the FileZilla client or WinSCP. If you have really large files, that's the way you have to do it. But there is a web interface here where you can upload your files. So you want to find the folder that your data files are in. So you'll have them located somewhere on your desktop. I don't know if I have the files located on my desktop, but I can just show an example. And then if you're logged in, you should find your username. So is everyone finding their username in the list of file folders over here on the left? Yes, no? Yeah? Yeah. Give people 5 minutes.
Yes.
Okay. Yeah, I know. Who of you is having trouble like moving the files into like the right place on your GNPS site? Okay. So maybe just as a general trick, how to like organize your files on your GNPS storage space here. If you want to bring order in that, I would recommend you to first generate a parent folder before you upload and drag and drop the files, right? So this you can do through this button here with like the new folder, right? So if in this case here, like Scott selected his like username as a folder and then adds like here, like a new folder, then a new window pops and we can like, you know, call this summer school test 2 or whatever. And then generate that. And now the question is, how do you select this folder for the files to be placed there? So similar, you have to basically just click on it, right? So that it's like here, like blue highlighted. And as soon as I do that, then it will move automatically the files in this place, right? So if I would, I don't know now, drag and drop whatever file that Scott might has here in his computer, then it would place it in this particular folder. All right, so we're just gonna download the data from scratch. So this is the task you should have done yesterday after you were done with MZMine. But yeah, if we go here to like the GitHub repository, to the MZMine output, and just like take here like this example file, I could download the MGF.
we have the pages.
So I just downloaded now the MGF file as a test again, right? And now it should be on Scott's desktop.
So there are a couple of questions online about like
Will you answer them on the chat?
I think it's relevant to people here too. It's like, where does the metadata come from?
Yeah.
And people need to, it's not an output, right? You need to generate.
I'll show it in a second. It is. It's just in a folder higher up. So if you go 2 steps back, there is a folder called metadata. I can show it in a second. Just struggling with the speed of this computer here. Apparently, there's too many files on the desktop. It's a good reminder. But yeah, somehow it's loaded now. Okay. Good. So I downloaded now this MGF into like this test folder, right? And now I have the file I need, and now I just need to drag and drop this into like that upload window. So this one, and then yeah, it's really important that you before mark like the folder where you want that file to be placed in, right? So now I'm just gonna take this MGF and I drag and drop it in here, and then magically it should appear. Now if I expand this, okay, well not yet. Let's see. We go to the input. So now you can see here under summer school test 2, there would be now the example MGF. And the same way you can do it with the quant table, with the IIN edges, as well as with the metadata file. So now some of you may wonder where the meta file is located, because it's not in the mzmine output files, right? Because this was some text file that were generated even before, because this contains like the experimental information from your data set. So it's also in the GitHub, it's just like higher up. Let me see if I can also find this. So here, if we go under the data folder, then there's a metadata subfolder. And then in there should be this metadata.txt. So it's a simple tab delimited text file, so you can open it in Excel if you want. And like I would actually recommend to like take a look at it later on as well, so you understand just the structure of this file.
Is there any columns that have to be there, or is it whatever?
Yes, that's actually a very good question. Let me download this really quick.
Yeah.
Oh. Okay, when I open this metadata file in the editor here, you'll see it's basically containing the file names of all the MZML files and then different attributes. And these attributes depend on your experimental design, right? So this can be group control versus knockout, or this can be time point, or replicate, or sample type, whatever. And there's one column that is required, and this is file name. And this needs to be all lower cap letters. And then it needs to be exactly the file names you use. So that's a thing that people often like mix up, and then it doesn't work. In theory, GNPS doesn't require it, so you could submit your job without the metadata, but obviously it makes it much nicer, if your data is already grouped, depending on your experimental context. So we strongly recommend using this unless you only have, I don't know, one file you want to analyze them. Obviously, you know already what all the metadata for that is. Okay, but yeah, for now, most importantly, you can upload this metadata file the same way through this drag and drop interface, right? So again, let me show you. You go here under upload files, and then select the folder where we want to upload this here. It needs to be blue highlighted, and then just drag and drop this file in here. And then, yeah, you would do the same with the quant table and the same with the IINHS file. And don't upload the serious MGF. First of all, because we don't need it right now. And then second, because it's larger than 20 megabytes, which is not supported by this web interface. So now, obviously, you may ask, what are we doing if we have files that are larger than 20 megabytes, especially dealing with the raw MZML files? That's typically the case. So then we recommend to use like an FTP client, such as like WinSCP or FileZilla, to actually upload this. It's a little bit, I think, more practical to use, but now for the time's sake and ease of use, we just quickly use like this web interface because it doesn't require you to install anything. So WinSCP is a little app. I saw many people had it already installed, right? So you can quickly install it. It's open source. But if you do not want to, you can also use this web interface. All right. Can I see some hands who managed to upload their files? Nice. Okay, who still struggles with uploading their files? All right, then I think we're gonna walk around and actually gonna help you. And then I think Scott can finish the job submission before we then talk a little bit about the background, what's going on under the hood while this job is processing. All right.
So we got back. Thanks, Daniel, for walking us through. We got back. Hopefully not everyone's data structure is as disorganized as mine is. So follow Daniel's advice for organizing your data. So everyone has their data uploaded, finish selection. We'll navigate back to, we have a second one open, so we need to make sure we get rid of that. And then here we are. So someone pointed out, you have your files here. You should have 4 files uploaded. Your metadata one doesn't appear here. It's just because there's not a prompt for it. But if you've uploaded it into the input screen, it's there. Yeah, and then these other fields, we don't have to play with. I can just show you just briefly. So here, like Robin was talking yesterday, the cosine similarity score match. If you want stricter matching parameters, you can increase your cosine similarity. You can decrease your match fragments. So if you know your compounds of interest you're hunting for are very small, they might not have a lot of fragments, we can drop this down. These are all the default settings. And all the examples and all the data we have, I've just run everything on default settings. That's how we're going to operate. But there's lots of drop-down fields here that you can play around with. You can add a filtering step to your data. There's a library search filter here. The default is that it searches the full GNPS spectral library. If you're doing targeted analysis, you can specify which library you want. If you're working with plants, you can find the plant library that's inside GNPS. So this is all defined. If you're doing drug metabolism, there's a drug library in here you want to search. But the default is it searches everything. I would just say just leave it as at that. Yeah. That's really it. And then you make sure you have your email selected down here. That way it sends you a notification when it's done. Usually these workflows are quite fast, 15, 20 minutes. Because we're 10 o'clock Europe time, North America is still asleep, so workflows are faster right now. But in the afternoon in Europe, they slow down because the guys in North America wake up and steal all the server space. So run your workflows in the morning. No. Yep, and then we just hit submit. So it will submit the workflow. You get this progress screen that comes up. It's doing some stuff in the background. Importantly, I always say, so you can obviously walk away from it, but your workflow tends, if there's a problem with it, you've put a file in the wrong location or something like this, it will fail within the first minute. So, or really it fails almost within the first 20 or 30 seconds. But just pay attention to it for the first minute or so, and if it's still operating, it's still running, so for instance, it's executed 34 seconds, still running, I would walk away now and be like, okay, it'll be done in 20 minutes. And it should be working.
Also, so you're all aware, you have like
Yep. Yeah. Yep. Correct. It's private to your account. So no one, yeah. So the other folders are either folders. So the question was any of the data that's uploaded into your server file, is it private? And the other, what are the other files that are present? So they're either just superfluous files. So for instance, you can access spectral libraries through some of those folders. Or for instance, in my inputs, I had actually pulled up some massive data sets. So you can actually go in, and if you have a massive data set you want to pull data from, you can say, pull that file, and then I can open it up and actually go in and click individual files in that massive data set. So there's another way to grab files. Yeah? Yeah.
If you upload the MDML file,
yeah.
What does that do if you don't actually need it?
Nothing. So it's essentially superfluous, I think. Uploading the MZML file with the MGF file, it's just it's a backup file essentially to some degree. Yeah. You can actually, I guess, add it into massive much more easily that way.
Yeah. So in general, I would recommend to upload your MZML files, because then you have like the nice thing that you can directly visualize them in the dashboard afterwards. Yeah. So we're not going too much into detail with that, but I think it's a good way to like link the MZML files, actually your raw spectra information, to your job. And then I may show you later quickly what you can do with it, but it basically gives you power to go directly back to the raw data and inspect it, which comes in very handy at the like validation stage. Okay. So who of you have their jobs running now? Okay. Who is still like struggling with like a couple of bits and bytes? All right. Nobody? Okay. So yeah, as I said, we're like around 150 people that now submitted a job. So I'm not sure if it's going to be done in 20 minutes. Let's hope. But yeah, worst case, we're just gonna do our coffee break like a little earlier and then quickly take a look at after the coffee break at the job, because we wanted to show you obviously now how your process data might look like. But yeah, while like the server is now doing their job and hopefully not crashing, we just want to talk very briefly again about what's actually happening under the hood right now. Right. I wish Robin was here to show me his trick how to move the Zoom bar. There's a no. Thank you, Camilla. Apparently, Robin was not needed. All right. So yeah, we want to briefly just recap what's actually going on right now in this data analysis. And yeah, we've talked on Monday about like the general data structure. So we have like the chromatography as one dimension. Then we like isolate like ions, fragment them, generate this MS2 spectra for like fingerprints, right? For like the molecules. And then we also have the like MS1 events next to it, right? In like this data dependent duty cycle. So we have like this combination of MS2 data and MS1 data. And yesterday, mainly what you did with EMSI-MINE was constructing this extracted ion chromatograms out of this MS1 data, right? And then today, we're kind of like mainly using like the MS2 spectra to now annotate what like these features are, right? So, and here, I think we've mentioned it a couple of times already, but we want to reiterate that this is like completely clear. So now we're looking at like this MS2 spectra, and we structure them by their spectral similarity. And I can imagine that it might be confusing to learn about like multiple tools that kind of like do similar things. But I want to like stress out again, like the concept that they have in common. And that is that both EMSI-MINE, what Robin did with the networking yesterday, and now what GNPS is doing is that it uses like this modified cosine score to basically establish the spectral similarity between like the MS-MS spectra, right? And then if like the score is above a certain threshold that you define in that job you just submitted, so the default for us was 0.7, then we establish like links between those spectra and then display them as nodes in these molecular networks, right? And now part of the annotation is that we also match the spectra against the spectral library. So you did this also in EMSI-MINE yesterday, and now GNPS is doing it too. And then we can annotate eventually some of those molecules as level 2 IDs, so putative annotations. And now what we can do with like the molecular networks is that we can propagate this annotation throughout the network. Because if you know that here, like this node F has like a library ID indicated through the star, and you know that there's like this other two nodes that are very similar based on their MS2 spectra, we generate a hypothesis that then the structure must be similar, and we know the structure of F through the library match, and then we can like basically say, okay, like E and G might be similar to this molecule. And this, for me as an analytical chemist or a natural product chemist, is very powerful because I see the delta mass between them. I eventually look at the structure, and then we see like these reoccurring mass patterns, like 14, right, for like a methyl group. And I can then say, okay, perhaps there's a methylation. And then if I have like a hydroxy group somewhere, and I know that in my gene cluster, there might be like a methyl transferase, then it's very like, yeah, like easy and straightforward to build up like this hypothesis. It's still putative, right? I still have to like eventually at the end do like the hard work and purify the compound and fully elucidate the 3D structure by NMR and eventually Marphase analysis and whatnot. But like it's very fast at the beginning to generate this hypothesis and get there. And yeah, I hope that that as a main take-home message you will like get. Okay, so now what did we do with like this MS1 data, right? So there's this MS2 level, and then there's this MS1 level. And yesterday, Stefan and Robin walked you through these different steps and a lot of settings in EMSI-MINE. And eventually, thanks to the batch wizard, we could create like this, hopefully like a little bit simplified version of like all like this different steps of raw data processing with it, right? But at the end, like the most important thing is that generated kind of like extracted ion chromatograms from this MS1 scans, from like your DDA, LC, MS data, and then at one point linked the MS2 information to each of like those MS1 chromatograms, right? So here again indicated through like the stars. And this is what feature-based molecular networking like builds up to, right? So it really connects like the semi-quant information from MS1 level, from those survey scans, from your DDA cycles, and then connects them to the MS2 level, right? And then this makes it, I think, much more like accurate when you want to like compare relative quantities between like samples, right? Because was only MS2 level, I mean, you could theoretically do that too. And as Scott pointed out, if you have a very simple question, you know, that might be the tool of choice. But obviously using sophisticated tools such as like MZMine or XCMS or other feature finding tools, you know, you get better semi-quant information. All right. Then we did not only use this MS1 data to actually like get this quant information, but also look at like different adducts. So this is buried in one of like the modules in MZMine ion identity networking, where we actually look at like co-eluding features that have like given mass differences. And that way easily we could say, hey, this is like M plus sodium, or this is M plus ammonium, you know, or might be even like an in-source fragment with a water loss, right? So here, think feature-based molecular networking, or actually ion identity molecular networking, not only establish connectivity based on like the MS2 level, but also on the MS1 level through like this co-elution profiles. So I think here, I think Robin pointed it out very nicely, you know, like it adds confidence. Because if you see like different adducts, right, and they all point to like the same M, then you know, okay, this is actually a sodium adduct, right? And this is like ammonia. And I'm pretty sure that this here must be M plus H plus, and thus this is the mass of actually M, right? And if you only look at one, then sometimes, especially in the higher mass range, this is ambiguous. Okay, so yeah, to IIN. So here, a perfect example, right? We have like our smallest peak actually M plus H plus. So this is what we most of the time actually want to see. But then, yeah, reality is there is a big ammonia adduct and a sodium adduct, and also some in-source fragments. And then, yeah, if you expand this, you can even annotate like more of supposedly artifacts. But to us, this is actually, you know, data that's just like backing each other up. Okay, so there has been a couple of papers like that you may have seen. So like these are like the first GNPS molecular networking paper, and then a very thorough protocols paper about the use of classic molecular networking, which I would recommend you to take a look. And then I want to stress out again, like the difference between classic molecular networking and feature-based molecular networking. So here we have a classic example where like classic molecular networking might not be like the best thing to do, because we have like in our sample A, kind of like 3 different like compounds that elute, and like in both 3 cases, they were abundant enough to actually, you know, make it through like the top N list of our DDA routine, and we get an MS event triggered. But then in the sample B here, the 3rd one was like too low, so this was not considered in our MS duty cycle. Hence, we don't have an MS spectra. So now if I would generate a classic molecular network, only comparing on MS2 level, then I would say, oh, actually the 3rd compound here is like not present in sample B. Hence, here the pie chart in the network only indicates abundance from sample A, blue. And yeah, as I showed you, if we have a feature-based molecular network where we combine this MS1 level feature finding and then connect it to MS2, then we get like better quantitative information. So yeah, these are, I think, the most recent papers, both the feature-based molecular networking paper as well as the ion identity networking paper. if you have not seen them, I would recommend to take a look at them. They describe like pretty much in detail what I just said. And then, yeah, like as another main take-home message, so there are two ways of generating molecular networks in GNPS, classic molecular networking as well as feature-based molecular networking. And what we did here was feature-based. If that all sounds too complicated to you, and you say, oh my gosh, I'm like completely overwhelmed with like this feature finding and like there's hundreds of settings, you know, then we actually often recommend collaboration partners or also new students in the lab to actually give classic molecular networking first a try. Because there you don't have to worry about any p-clicking, and you just like basically dump your MZML files into GNPS, and it creates like this, yeah, like simplified molecular network only on MS2 level. But again, yeah, it's a question, you know, you first of all want to get like the analysis done, right? And if you struggle with the settings and you won't manage to go all the way through, then yeah, go back to classic molecular networking. If you have a very simple question, right? Often like in natural product research, we do not have like complicated treatment groups, and we don't need to like figure out like this 5% differences in metabolite levels, right? Then maybe classic molecular networking is good enough. And to me, as a general check of my data, when it comes from the machine and I want to just see, okay, does that look good? Do I ID anything out of it? You know, I quickly run some classic molecular networks because I'm not losing MS2 spectra by actually doing like this pairing, right? I'm really considering all the data that is there. So I think there's good reasons to use both approaches. Obviously, like now for like the workshop and this advanced data analysis we can perform with you, I think feature-based molecular networking is the way, but yeah, be aware that there's also this alternative. All right, I think I've talked enough about the differences. Very importantly, we have extensive documentation online. So actually, if you're like on this GNPS site, there's like this documentation button at the top. And then, yeah, like a lot of people spend a lot of time writing detailed documentations for all like the different workflows. So if you get lost, feel free to take a look in there as well. And hopefully it's easy enough to, even without the workshop or without the recordings later, you know, like to guide you through the analysis. And yeah, I think that's pretty much it. I hope that you by now have gotten an email from the GNPS server that said that your job was done, and then there should be like a long link like this in there, which you then can like click on, and then we can actually open that job. If this is not the case, I would recommend we just like do the coffee break now, and then hopefully after the coffee break, look at this job. So who got email? Was the job being done?
It's still running back.
All right. Then I would say let's enjoy some coffee, and then after the coffee break,
Did have a question?
continue.
Someone